differential geometry has long had a home in physics. It is kind of where it laid the foundation for deriving equations of special and general relativity, especially general relativity. But more and more, it's finding a home in mechanical engineering. Broadly speaking, what you're thinking about are what are referred to as manifolds or kind of surfaces or stacks of surfaces that are kind of locally at an infinitesimal level flat, but then might be curved away from that infinitesimal point. And the goal of this little 2-day dive into this topic is not to, again, make you proficient in this subject. It is to kind of give you the language and some of the concepts that you would need to dive into this topic. I'm trying to make it as conceptual as possible. And so, but, in order for it to be as conceptual as possible, I'm going to need you in these next 2 lectures to be willing and able to jump in with questions about if something is making sense or not, because I think this will be the most non-intuitive probably topic that we cover, and without your kind of feedback on this, I'll have a hard time kind of knowing if everything is making sense or if you're just completely lost. And so I would encourage you to please interrupt with questions. I think the concepts in this can be really quite challenging, and in particular, the notation can be quite challenging. If you have a background in physics, the notation will not bother you. If you have taken classes in continuum mechanics or elasticity, you're bound to be annoyed by the notation that we discuss here. And the reason for that is that most of the time mechanical engineers learn continuum mechanics and elasticity, and they do it all based on living in flat space, what we call Euclidean space. X, Y, and Z, the corner of a room being the coordinate system that you're working on. And if you're in that space, a lot of the notation that I'm about to show you reduces in a particular way. I found that confounding at first when I started learning this topic, but I now almost kind of can't look at continuum mechanics notation without wanting to write it in this more general form. I find it much more intuitive now that I've spent time with it, but I don't think that that'll happen immediately. So what do we care about differential geometry as mechanical engineers? For one reason is it allows us to think about large deformations, large changes in shape. It allows us to kind of put some math behind the surfaces that an array of quadcopters might be moving between, or the shape of an individual strand of DNA, which what we're going to concern ourselves with is something very similar to what we think about with an elastica, which is a coordinate system that's running along the curve of that shape. It allows us to think about things like bubbles and droplets, which are spherical or curved by their nature. And also it allows us to think about structures that are thin, like plates and shells, and how those structures change shape. This area of kind of large deformations and kind of large changes in things is really important as well on the biological side. If you're thinking about kind of biological growth, in which it doesn't make a ton of sense to think about infinitesimal changes between state A and state B when there's been a significant change between these two quantities. How do you account for that change in geometry? The overall motivation for these tools of differential geometry is really simple to state, and it is that the laws of physics that govern all of the things I just talked about, from the shape of a DNA strand to a spherical blood cell to the orbits of planets around a star, all of these physical laws should be invariant. They should not vary depending on the observer. So the coordinate system we put on these physical laws in order to solve them and do calculations is arbitrary. We just pick a coordinate system that's convenient for us, but you might pick a different coordinate system than I might, based on the fact that I'm looking at this a different way, or I think this is easier than that. And our physical laws should be identical regardless of our choice of our coordinate system. And that concept of invariance is what motivates this topic, as we are trying to kind of map between different coordinate systems, map between different geometries that are kind of convected onto those shape changes. There's kind of three things that I would like for us to cover in order to give you a sense of this field. First is, if we are able to say that something is invariant, then we should be able to transform a physical quantity from one coordinate system to another. And you've done this many a times throughout your career, but if you're anything like how I've encountered this at lower levels of engineering, it's very ad hoc, and you kind of do it as needed for calculating something in cylindrical coordinates or spherical coordinates. And so one of the things we're going to talk about in terms of invariance, and this kind of first chunk of time we're going to spend is really talking about tensors. And tensors are something that is another kind of area that tends to scare off people. But in order to understand differential geometry, we have to be able to think about tensors and how these kind of physical objects transform as we switch coordinate systems. So the first thing we're going to do is think about transformations. Second thing we're going to do is think about how do we measure stuff when we're in one system versus another. And the third thing we're going to do is try to think about curved space and how do we do calculus in curved space. Like I said, this is going to be high level and kind of fast. And so please interrupt with questions. I expect there will be lots of them. And so if there are not, I'll be confused. All right. So we're motivated by this concept that physical laws should be invariant. They shouldn't change depending on how the observer is looking at something or the reference frame that we are studying the system in. And physical quantities, we're often interested in how the physical quantities transform as we switch coordinate systems. And some things don't change as we switch coordinate systems. Scalars are a perfect example of that you're comfortable with. Things like energy and mass are things that are not going to be affected as we change the coordinate system. But as we know, things like vectors and tensors, the vectors and tensors themselves are not going to change, because those are kind of true physical quantities that exist in the world. But the way we measure them might. And so the thing we have to concern ourselves with is what happens as we change coordinates. So to get at this topic, my overview for this lecture is going to, or these next two lectures, is going to be talking about transformations. And to do so, we have to learn a little bit about tensors. Talking about measuring. and talking about curved spaces. So these are the three topics that I want us to cover. And it's going to be fast, and I apologize. But my goal, as I've said, is let me give you kind of the concepts that will at least make this less intimidating when you come across it again. So let's start with something that we've done probably hundreds of times in our career as engineers, and that is transforming from Cartesian to polar coordinates. And so our Cartesian coordinates, we'll just do this in 2D for simplicity, but this all works in 3D, of course. Means we're going to transform from something that's measured in x and y to something that's going to be measured in r theta. Now, typically when you have a coordinate system that you're trying to transform into, you have some way of parameterizing those coordinates. And the way that we parameterize polar coordinates is probably familiar to you. It's saying that, well, we can write x as our coordinate r times the cosine of theta, and we can write y as r sine theta. And what we're interested in is going to be the differentials in these coordinate systems. And so instead of being interested in x, what we want to think about is dx, and we want to think about dy. And so to think about dx and dy, what we have to do is use the product rule to evaluate our parameterization here. So if we take x here, and from the product rule, we can say that this should be equal to the derivative, the infinitesimal of r times cosine theta minus the infinitesimal d theta times r sine theta. The minus sign comes up from the derivative of the cosine, and everything else is pretty straightforward, I hope. Similarly, we can look at the infinitesimals in y and do the same thing, expanding this with the product rule. Dr sine theta minus d theta, plus d theta r cos theta. Okay, and so again, I'm going to start hinting at some of the things that I've talked about as our overview here. But in transforming between coordinate systems, it's important for you to be able to know, how do we measure stuff in that new coordinate system? How do we measure something? And the most fundamental thing you can measure is distance. And you're familiar with the idea of how you measure a Euclidean distance, right? It's going to be the square root of the distances in the x direction squared plus the distance in the y direction squared. And thinking about Euclidean distance, no one likes radicals, so we oftentimes write this out without dealing with the square root at all. So we might say, well, let's just think of our incremental distance, ds squared. That's going to be our length in our coordinate system. And our length in Cartesian coordinates, we just said what it was. The Euclidean distance is going to be dx squared plus dy squared. So now we have things that we can substitute in for dx and dy. And so if this is the distance or the length of a line element in Euclidean space, then the length of a line element in polar coordinates is going to look like, let's see here, we have to square dx, so it's going to be dr cos theta minus r sine theta d theta, I just moved that around, squared plus dr sine theta plus r cos theta d theta squared. Now you can expand this out. You have squared terms here, and if you remember some trigonometric identities that say the sine squared plus cosine squared equals 1, what you'll find after some algebra and geometry is that this reduces really quite a lot to something nice and compact. And it reduces to that the line element in polar coordinates is going to just be dr squared plus r squared d theta squared. And what I want to point out here is that this line element is made up of a sum, in this case of 2 components, because we're only looking in 2D. If we were in 3D, it would be 3 components. If we're doing space-time, it would be 4 components. But in this case, it's the sum of 2 things, 2 quantities. And those quantities consist of kind of 2 components. The first component is the differential, or the infinitesimal here, this d something. And the second component is whatever is multiplying our infinitesimal coordinate. So I'll highlight that in pink. We can generalize this by kind of recognizing that we don't need to make our life difficult and carry around all sorts of different symbols here for our differentials. We can just say, well, in my coordinate system, I only have kind of two components. So I can write something like, let's see here. Let's see this over here. I can say, let's call our coordinates x to the mu, or this could be x1, x2, as many times as we need, times x to whatever dimension our space is in. Now, in this particular example I just gave you, let's say we were using green here, x1 would consist of r, and x2 would consist of theta. In Euclidean space, x1 would be x and x2 would be y. In spherical coordinates, there's going to be a phi in there. This is a kind of a way that we can start to make our notation more compact.
Is there a reason to use superscripts instead of subscripts? Is that just the notation?
There is a very, very important reason, and we will spend quite a bit of time talking about the meaning of superscripts and subscripts here. And it's kind of the hallmark of tensor analysis, and it's also the thing that gives most students heartburn when thinking about it until they get kind of comfortable with it. And I will give me like 2 minutes and we'll talk in great detail about what the role of these upper and lower indices will be. So what we can do is we can now say we have a way of talking about our coordinates. And what we would like to be able to do is have a way of talking about the kind of coefficients that multiply these coordinates. And these coefficients that multiply these coordinates are related to the basis vectors in the coordinate system that you've chosen. And let me first show you what the notation looks like. And then I will unpack it a little bit and I'll talk about how this relates to stuff that's probably more familiar to you. So we can, in general, write any line element as the sum of our coordinates from mu is equal to 1 to whatever dimensionality we have, in this case 2, times the sum of, let's pick another one. Let's go with nu from 1 to d times something. I'm going to call it g, which has the subscripts of mu and nu, times our infinitesimals dx mu, dx nu. Now let me just highlight some things here. This quantity is going to contain all the stuff in pink above, and these quantities are our coordinates. Now you'll notice that the thing on the left-hand side it's the length of a line. This quantity is invariant. This quantity also has no superscripts or subscripts. To be clear, this is a squared quantity, which is different than a superscript, and we'll kind of talk about that. Usually we'll kind of wrap that in braces, so you don't have to worry about thinking about if it's a superscript or a power. But for right now, just kind of hold that off in your mind. So this is a scalar, and on the right-hand side, what you notice is you have some quantities that you don't know what the heck to do with. But you'll notice that in the product here, I have a mu that's downstairs and a mu that's upstairs, and a nu that's downstairs and a mu that's upstairs. The fact that those things are kind of downstairs and upstairs is going to do a couple things. They're going to what's called contract. Now, most people, when they're starting to learn about tensor analysis, will kind of think of contraction as a canceling out. I will say it's one of those double-edged swords of it's a helpful way for you to think about it, and it's also mathematically the incorrect terminology. But for right now, what I want you to notice is that if I have a product, this is all one product, right? Let me write this in red. This is all one product of 3 terms. And if I have in that product matching indices, upstairs and downstairs, those things will contract, and you will not see that index on the left-hand side. So mu is on the downstairs and upstairs. You won't see mu on the left-hand side of the equation. Nu is on the downstairs and upstairs. You won't see nu on the left-hand side of the equation. This notation can be made even more compact if you introduce Einstein's summation notation. This would be familiar to you if you've done something in continuum mechanics. The only difference is, and to me, I think this is a far superior way to think about this. The only difference is our summation notation in tensor analysis, you always sum over indices that are the same letter, and one is upstairs and one's downstairs. In typical Einstein notation in Euclidean space where everything's flat, you just have to have the same index in the same term. Here, we require one to be upstairs, one to be downstairs. So we can get rid of those pesky summations and just write this as g mu nu times dx mu dx nu. This is what is known as the first fundamental form. And this quantity here has a really, really, really important role in physics and mechanics. It is the metric tensor. How do we think about what the metric tensor is? So let's bring this I'm kind of working in this space where everything is probably unfamiliar and weird, and that's okay. I'm going to try to pull it back and land this plane. The metric tensor is constructed from the basis vectors in your coordinate system. So you remember your basis vectors, right? You have something that's like x and y, or x1 and x2. And then on each of these, you could imagine a unit vector which we can call this like I hat. I hat 1, or you might normally think of this as I and j. We're going to keep our notation similar here, so we'll call this one I hat 2. Unit vectors are just vectors of length 1. Basis vectors are a set of linearly independent vectors that, when used, can represent any vector in a vector space. So by adding up, you can write any vector that you write. So hey, I'm going to put my little imaginary arrow on here, and I can tell you properties of that arrow based on kind of how many basis vectors do I need in each direction to kind of, for instance, tell me the length of this vector v. And so I need to go a certain number of I1s to the in the x1 direction, and a certain number of I2s in the y direction. So how does this relate to what we're talking about with our metric tensor? Well, let's unpack this thing. Our metric tensor is constructed by taking the dot product between our two basis vectors. So for instance, I can take the dot product between g mu and g nu. Nothing here is upstairs. These are both subscripts, and so there's nothing we can do. The result of that dot product is just another, this is a vector. Let me see if I can find some stuff out. This is a vector. This is a vector. The result of dotting these two vectors where both components are downstairs is a tensor with both components being downstairs. What on earth are these G vector things here that I've just written down? Those are your basis vectors. So for instance, G mu might be I hat 1. Oops, that's not a 1. And G nu might be, in the case of polar coordinates, R times I hat 2. So what is our equation here telling us? Our equation here up here is telling us that the length of a line in our space here is made up of this tensor times the infinitesimals in each direction. Yep, Reese.
Okay. Sorry. So.
No, there's
things. Yeah.
Yeah.
Okay. So first off, going back to our metric tensor and the discussion of like Einstein's summation notation. I feel like when I was taught it, there was like discussion about summing over 3 indices. I'm assuming that can be more general to more indices than that.
Yep.
And then the other thing was that the repeated indices that you sum over, is it true that we are limiting that to only be 2 indices that we're summing over? Or could we have a third mu, for example, that we did sum over? Those are kind of the 2 things that we talked about.
Sure. So the first question is straightforward, and you can see it here. The first question is right here. In continuum mechanics, this sum is always over 3. You're saying, I'm in 3D space, I can sum over 1, 2, and 3, x, y, and z, and you're fine. In general, it can be more than 3. If you work in lipids and vesicles and shells and plates, it's usually 2 dimensions. You're kind of living on a surface. If you're doing a 3D elasticity, continuum mechanics problems, it's usually 3 dimensions. So you're usually summing over x, y, and z, or r, theta, phi. If you're doing general relativity, it's usually 4 dimensions. You're doing the 3 spatial dimensions and a time dimension. It can, in principle, be as many as you want. You can just pick your dimensionality of your system. I've never encountered more than 4, and the only things I practically use this stuff for is 2 and 3. The second thing is you can only sum over indices that are upstairs and downstairs, and so they kind of have to go together. So you can have, in each product, you can have like a mu downstairs and a mu upstairs, but you can't have another one downstairs somewhere else. So you would have to have a different symbol on that one. So you really are just looking for kind of pairs of these things that are upstairs and downstairs.
Okay.
That.
Yeah,
Yeah.
no. And then the other question I had, so now looking at this dot product that we did with the 2 indices downstairs, is that analogous to like a tensor product, a dyadic product?
Yep, exactly. Oh. It's exactly correct. Yep.
Got it.
Mm-hmm. Okay, so I need to keep unpacking this to give you some sense of what's happening here. So the metric tensor in flat space, and the reason why all this stuff is really simple when you're doing things in Euclidean geometry is look up here. This has got a prefactor of 1. This has got a prefactor of 1. So the metric tensor, G mu nu, in flat space is exactly equal to Kroneker's delta, or the identity matrix. So in 2 dimensions, Kroneker's delta looks like this. Now, again, you're probably used to seeing Kroneker's delta if you're taking a continuum mechanics course with both of them downstairs. Here in tensor analysis, one of them lives upstairs. It doesn't actually matter because this thing is equal to I if you prefer matrix notation, and this thing is equal to 1, 1, 0, 0. And so you can think of this equation as saying, where's my equation? Yeah, you can think of this in Cartesian coordinates as saying, let's see here. I'm going to take 1, 1, 0, 0, and multiply that by my column vector dx, dy. And you should be able to see fairly quickly that this is going to tell me it's going to give me something that's like dx squared. Where's the squared come in? Oh, that's because this is dx, dx, dx. Okay, perfect. So this will be dx squared plus dy squared. And it's because you have this product here. Oops. You can also see why you don't have any mixed components. You don't see a dx dy because the metric tensor has no components in the off diagonal. So if I'm giving you this,
quick question.
Yep.
How did it become squared again?
Because it's saying take this matrix and multiply it by. I think I wrote it down in my vector form incorrectly. It's saying take this matrix and multiply it by the dx1 dx times dx1, and then add that to. Let me see if I can do this out. Hold on. let's do this out more explicitly. Give me one
Oh,
second.
the dx dy is just a
Exactly.
representation of dx to the mu or something.
Yeah, give me 1 second. I kind of sloppily wrote down that column vector, and of course, I should not have. One second. Okay, cool. Here we go. Of course, we want to see the paper right in front of me. So let me do this out properly. So for Euclidean space, I'm just going to erase this so that way I kind of make this more. We do it all as formally as possible. So what this is saying is take the, let's see, now these are just the indexes that we can put in numbers for. So we can say, let's take the G11 component of our metric tensor and multiply that by dx1 times dx1. Add to that my G12 times dx1 dx2. Add to that my G21 times dx2 dx1. Add to that G22 dx2 dx2. So now, knowing that the metric tensor in Euclidean space in 2D is just the identity matrix, it's just 1 and 1, then we would say that this term is 0, this term is 0, this term is dx, this term is dx, so the product of that is dx squared, this is dy, dy, and then this is 1, this is 1. And so we recover what we're used to, which is now. So does that help understand the way to unpack the first fundamental form, that the length of the line?
Yeah, makes sense.
So if the metric tensor is composed of dotting the two basis vectors together in 2D, then if these are our two basis vectors in polar coordinates, polar, then the metric tensor in polar coordinates is what? This thing is just a 1 in front of that, so it's just going to be a 1. We're still going to have nothing in the mixed direction, and then here we're going to have an R appearing. And so we can do the same thing. We can say, well, now I have a different metric tensor. I'm writing it in red here. And so in polar coordinates, I would get my length of my line is going to be G11. It's going to be 1 times dr squared. These are still 0. And then my third term becomes r squared times d theta squared. So it's now time to talk about conceptually, what is this metric tensor doing? And the metric tensor, and we'll kind of come back to this a little bit. The metric tensor allows us to determine lengths and angles between, say, tangent vectors. It also is a lot more powerful, can do things to help us with equations, but that we will kind of put that on hold for a second. The thing I want to say is that tensors, like the metric tensor, they don't change when you change coordinate systems. What changes is the components of the tensor. What changes is the stuff inside the matrix here. Whether or not it's this thing here, which is 1 and a 1, and this thing here, which is a 1 and an r squared. Tensors do not change under transformation. Their components do. So now it's time to talk about what these upper and lower indices represent and why we keep track of them. And we keep track of them because we are interested in going back to this idea of physical laws should be invariant. As I change from one coordinate system to the other, I need to know how the quantities that I'm looking at or measuring, how do they change when I change coordinate systems? To say that more formally, what we're interested in is how do these quantities transform as we transform our coordinate system? And there are more technical terms you might be surprised to learn than upstairs and downstairs. Those more technical terms are, we refer to the, actually I'm going to do this the other way around. We refer to the upper indices as contravariant. And we refer to the lower indices as covariant. And the key thing here is as we transform this object, do the things that we're interested in, maybe the vectors or the tensors that we're measuring, do they change in a way similar to how we're transforming them? Do they co-vary with our change of coordinates or change our basis vectors? Or do they contravary? Do they vary in an opposite way with our coordinate, with a change in our basis vectors? Here's the, perhaps, hopefully, the simplest way to think about the difference between the way these two vectors change. If I am measuring velocity in terms of meters per second, velocity, as we know, is a vector. And I'm measuring it in a basis that is describing length in terms of meters per second. If I was to change that basis that I'm measuring my velocity in, and say I would like us to now measure velocity in terms of centimeters per second, what I would be doing is I would be taking my basis vector and dividing it by 100. Going from meters to centimeters. So I've taken my basis vector and I've divided it by 100. If I do so, does my velocity get cut in half by 100 or multiplied by 100? Multiplied, right? So as I change my basis vectors from meters to 100 to centimeters, I'm dividing my basis vectors, and I'm having the opposite effect on the physical quantity of velocity. So I went from 1 meter per second to 100 centimeters per second. The vector itself didn't change. It's still the same velocity. But the components of that vector changed because now we're measuring it with a different basis. And because that number varied in an opposite manner to how we change the way we're measuring it, it went up as our basis went down, we would say that that velocity vector is contravariant. And in general, contravariant vectors typically have length appearing in the numerator. So things that measure displacement, velocity, acceleration, these are all typically measured as contravariant tensors. In the more linear algebra sense of things, you would think of these would be represented as column vectors. And the important thing and what defines them is how they transform. When you change the basis, how does that tensor change? If it changes in the same way as your basis, then it's covariant. And if it changes in the opposite way as your basis, then it's contravariant. So if having length in the numerator of your tensor or vector that you're measuring typically gives you a contravariant vector, then having length in the denominator is going to give you a covariant vector. These are trickier, and what you typically see here are more functions and operators. For instance, the most classic example of a covariant tensor is really like a differential operator, and it's the gradient. Another, trying to give you as many terms as I can think of here. These contravariant vectors here are also thought of as tangent vectors, while your covariant ones are often thought of as row vectors. And these have this kind of awful name of covectors. Not awful, but probably unfamiliar name, I should say. So how is the gradient a covariant tensor? So if you think about, for me, I think perhaps the simplest way, it's not as simple as the velocity thing, is to think about a contour map. And to think about how a contour map is usually drawn with kind of circles or contours that denote if we're thinking about like a topographical map, it would maybe dictating, it might be measuring heights of features, geographic features. And the closer those heights, those rings are together, kind of the steeper that slope is. And what you're doing is kind of looking at the gradient or the slope of that hill. And if you were to say stretch out that map and kind of stretch it in one direction, for instance, if you've ever seen, I'm sure you all have, the Mercator projection of a map of the Earth, you know that Antarctica and Greenland get stretched massively in that projection of the Earth when they're actually quite small, but because of how that map is drawn, they get stretched quite a bit. As you stretch Greenland, the contours of that map that dictate kind of the gradient of slopes there are also going to get stretched out in the same manner. Those lines that dictate those contours saying how steep something is on that contour map are going to get further and further spaced apart because you've stretched all your distances there. So therefore you've stretched kind of the slopes that you're measuring, the steepness of that geography. So those contours co-vary with your change of basis. Okay. When you multiply when you're kind of taking a vector that is contravariant with a vector that is covariant, you're actually doing something that is very familiar to you, even if it might not seem like it. And what you're doing is, so if I take my arbitrary vector A, and I take it, it's got some components that are covariant, we'll call it lambda, and I multiply that by B using the same same variable for our superscript. As we've said before, when you have something downstairs and something upstairs of the same type, then that will no longer appear on the on the other side of your equation. What you've done is you've taken those tensor components and you've contracted them, and you've kind of gotten some scalar or quantity of information out of it. So what on earth is that scalar that you get out of this? You're going to get something here, we'll call it C. And you'll notice that there are no subscripts on that. This has one subscript. So it's what's referred to as a vector or a 0th order tensor, because vectors are just tensors. And this is also a vector. And what you're doing is you're actually simply dotting those two vectors together. This is the form of the dot product kind of in some arbitrary manifold. And so the result of dotting A into B is you get some scalar out. What's that scalar? It's going to be some relation of the angle between those two vectors. You kind of taken a, if you dot the vector into itself, you end up recovering your kind of identity matrix. So this ability to kind of contract tensors and vectors together to extract some sort of physical interpretation of what you're actually measuring. So remember how I said your metric tensor allows you to measure distances. So if I walk this way and this way, how far did I go? Well, you need to know how many steps did I take in that direction and how many steps did I take in that direction. The metric tensor tells you how to measure and how to add up those steps based on your kind of your basis vectors in one direction plus your basis vectors in your other direction. And then taking vectors in that space and dotting them into each other allows you to measure angles within that space. So this, your metric tensor is allowing you to measure lengths and angles in whatever coordinate system you're in. Okay, it's time for questions.
On the metric tensor, say if we take the example of the one you wrote in red over there, how would you, yeah, that one, how would you distribute, say, I hat components across all four of those elements? Would you call, if the two anti-diagonal elements weren't zero, would they be I hat 1 dotted with I hat 2, or would they be their own I hat?
Nope, you're correct.
They'd be I hat 1.
Yeah, you're dotting them into each other, which is why you get the R squared term there.
So
you're dotting I2 into I2, and so
visually you could almost, at least in that example, draw it as a table where the top row title or header is I had one, I had two, and then same thing for the other header thing, and then each entry is like the dot products. Okay.
That's exactly right.
And then how does that generalize back to the notations? Because I'm struggling to. Oh, so each dx to whatever corresponds to a given component.
I think I lost you a little bit in that last remark there. Each dx, whatever corresponds to.
So dx to the 1 corresponds to, or dx to the mu corresponds to I hat 1, dx to the v corresponds to I hat 2, and so on and so forth, or x.
Yeah, so I think the way to think about that is, here you're saying, okay, I have to sum over m and I have to sum over nu, right? Because that's what this says. I have to sum over m, I have to sum over nu from 1 to d, from 1 to d. So when you go back here, and say d is 2, then I have to put in, everywhere I see mu, I put in 1. Everywhere you see nu, I put in 1. And then I just kind of go forth and do that for every permutation of it. All right, I have mu1, nu 2, mu2, nu1. Should have picked ones that don't rhyme.
Yeah,
but yeah, exactly.
That, like, implementing that makes sense. I guess I'm just trying to back up one more step and understand the formalism about the components. Like, so if I were to write that Einstein notation version of it, where would I stick my I hats 1 through D or something?
Well, what happens if you dot your basis vector into itself?
Sure.
So you get 1, right?
Yeah.
And if you dot your basis vector into the opposite basis vector, you're going to get 0. And so the I hat, the basis vectors, due to like the orthogonality of them, will disappear. Not disappear. They will adopt 1 or 0 kind of as you dot them into each other. Is that helping?
So are the basis vectors themselves contained in the metric tensor, or are they contained in the
yeah, the basis vectors basically are dotted. So here, I don't want to say that. When you dot the basis vectors into each other, those, it's kind of what we're doing right here.
Oh, okay.
This thing is this. So when dotting them into each other, you get this object. But along the way, you're kind of dotting I hat 1 into I hat 1, I hat 1 into I hat 2, and so on and so forth.
Okay, I see. Thanks.
Some of this is kind of has popped up in the past for you, and you probably learned about it in a different way. But for instance, let's think back to multivariate calculus. And let's say let's think back to multivariate calculus and say, I would like to do a volume integral. You kind of naively would say that my volume is going to be the integral of dx, dy, dz, which is the triple integral, obviously, along each of these differentials. But it's probably one of the main things you remember from multivariate calculus is that you can't just switch dx with dr, dy with d theta and dz with d phi, right? You have to kind of, additional terms pop up and you probably memorize them. But if you, in general, know that the volume integral is going to be equal to let me do this a different way. In general, the volume integral is going to be equal to the determinant of your metric tensor. So that's what I'm writing here with my vertical lines, with the square root of the determinant of the metric tensor. Let me write that down. Then you immediately recover the ability to do your volume or your area integrals in whatever coordinate system you want. Okay, so let's take a detour here. So what is this? Let's unpack this thing. So G. So in polar coordinates, we know that G, I'm picking different subscripts. I can call them whatever letters I want. I'm going to call that 1 and r squared, 0, 0. This is my metric tensor in polar coordinates. So if I want to calculate the volume integral in polar coordinates, I guess it would be, I can't really do that. It's like an area integral. Let me do it. Let's do it in spherical coordinates. Sorry. So we actually can do a volume integral. 0, 0, 0. So in spherical coordinates, you'll just have to take my word for this right now. We can derive it together if you're interested in later. In spherical coordinates, your metric tensor looks like this. Metric tensor in spherical coordinates. So this is telling me that in order to take this volume integral, I need to calculate the determinant of G and then take the square root of that. This thing has a particular name, doesn't really matter, but it's called the scalar density. This determinant is pretty easy to calculate. It's going to be r to the 4th times sine squared theta. There's no off diagonal terms at all, so the determinant is pretty trivial. And we now have to calculate the scalar density, which is the square root of the determinant of G. And so that becomes r squared sine theta. And so now if you were to calculate the volume integral in spherical coordinates, you would write r squared sine theta d, what do we talk about? We do d r d theta d phi. And you immediately get the proper way to calculate your volume integral in that coordinate system. If you were to do an area integral in polar coordinates, again, you would be looking at the scalar density times the infinitesimals in that coordinate system. And so these quantities that you've learned about in multivariate calculus are coming from questions of how do I measure stuff in this coordinate system, right? How do I measure area? How do I measure volume? To measure volume, you have to account for the space that you're living in. Is this like, I don't know, I remember the first time I learned this, I thought that was kind of cool, but I don't know. These quantities and these generalizations help us kind of think about how to measure things using different reference frames, using different coordinates. Because we know that the volume of our object should not depend on the coordinate system that we're measuring it in, but we need to be able to figure out how to calculate that quantity in whatever coordinate system we're working on our problem. More questions? Yep. Thanks.
Are we taking the positive of that square root, the absolute value?
The vertical lines were meant to denote, is that actually absolute value of the determinant of G? I think it might be. I think it might be absolute value of the determinant of G, which is why the G appears with no subscripts, because that's typically how you write determinant in tensor notation.
No, I meant on the outside of the square root.
On the outside of the square
So
root.
like absolute value of the square root of the determinant.
To indicate that properly, shouldn't it just be a double line on the inside?
Yeah, but it's not a double line, so I'm trying to think if that's.
Oh.
I know for sure it's with single vertical lines, and so
Does that imply if the basis vectors in G, if any of them are negative, or if the determinant comes out negative, then you go into like some imaginary space?
Yeah, it must. I guess it must be absolute value then, because like all of the metric tensors in like general relativity always have one or three components that are negative, and so if you want to calculate volume there, you would always get a negative quantity appearing in that determinant. So it must be absolute value of the determinant of G. Yeah,
Okay.
I'll double check that, but I think that's correct.
Okay.
How are we doing? This is a good sign. I hope. Let me do some basic stuff with tensors now. Let's just make sure that we're all on the same page. So if you see a quantity written with no subscripts, then it is determined a scalar. I think I was incorrect up here. I think I called these zeroth order tensors. I think I meant to say these are first order. Sorry. That's better. So a scalar is a zeroth order tensor, if you want. A vector is a first order. It's got one subscript. What you're used to thinking of as a tensor is something with two subscripts. And that's more formally a second order tensor. If you're not used to thinking about second order tensors, things like stress and well, the metric tensor are second order tensors. You can keep going. So we could say dijk would be a third order tensor. This is if you've taken continuum mechanics, there is one really important third order tensor that you encounter, and that is the Levi-Civita permutation tensor, which would be written as epsilon ijk. is equal to negative epsilon. If you don't know what this is, it doesn't matter. It'll help you at some point in your life if you take continuum mechanics. If you do know what this is, it's just I'm just letting you know that it's a third order tensor. And it's a permutation tensor that allows you to kind of like, kind of shuffle around the indices of your tensors and appropriately account for, say, what you're measuring or calculating. These things can be constructed or just they can just appear in the same way as anything else. If I take a second order tensor and then I multiply it by a third order tensor, a first order tensor, I clearly have none of the same indices, so there's going to be no contraction. Nothing's appearing in the upstairs that's going to allow us to contract variables. And this could be written as, let's go with a different, I'll go with D. We'll call it D, I, J, K. There's a fourth order tensor, which is also really important in, let's not use E, let's use F, I, J, K, L. And this is most commonly encountered if you're taking elasticity. This is the elastic modulus tensor. You might remember, if you've taken any elasticity, you might remember that you see stuff like stress, Ij, is equal to strain, KL, and there needs to be some sort of a Ij, KL here. So the KLs will contract, you'll be left with an Ij on the left-hand side, and you end up with something that looks like this quantity here. One of the things that I really like about tensor analysis is it allows you to almost immediately check the validity of an equation. So for instance, I can just start making stuff up. So valid tensor equations. So I could say, let me take R, I, L, I'm just making up stuff here, times S to the L, M, N, times T to the N, times U to the M, K. Like, this is just making stuff up. But we can do, so we can say, well, I have an L and an L here. So I know that an L can't appear on the other side of my equation. I have a N and an N here. So that can't appear on the other side of the equation. I should have done that in a different color. N and an N, that can't appear on the other side of the equation. We'll go M and an M, can't appear on the other side of the equation. All of these things are contracting. And the end result of this will be some other quantity. Let's call it, we'll call it V. And we know that it has to look like this. It has to. Otherwise, you don't have a valid equation. This is really powerful if you're trying to go through calculations really quickly, and you can kind of immediately identify what is this correct? What do I do? You know that any time you have one term which contains the same symbol as a covariant and a contravariant component, that will contract, and you will not see that component appearing on the other side of the equation. Does this make sense? This is really important. If you ever work on a problem of differential geometry, I promise you'll make a mistake. And I promise you'll be so annoyed at how quickly your collaborator or professor says that equation's wrong. And you're going to be like, how on earth? You just looked at it for 4 seconds. How do you know that? And you can see it from kind of like I don't know, it almost like jumps out. It's like a scratching nails on a chalkboard. Like if I see like an L on the right-hand side of this equation, like it would just be wrong. Like, and so getting comfortable with this way that these tensor equations look and work is really, really helpful.
Does the order matter?
I think if I understand what you're asking, you're basically saying if I had this same equation.
No. If your term SLMN, if that entire term, instead of moving you kept the LM and N in the upper part, but you just moved that entire S term to the beginning, and RIL was in the middle, or UMK was somewhere else. Yeah.
Yeah, no, it doesn't. Yep. Not for these. And not only that, but you can actually also interchange for symmetric tensors, you can interchange the location of the indices, just like you can in like continuum mechanics and elasticity. So if you have a symmetric tensor, then that's still true. So not only does the order of the tensor in the equation not matter, if you have a symmetric tensor, the order of the indices can be swapped.
But you can't swap if a component is in the top portion, you can't move it to the down portion.
It's like I was going to, yes, awesome. So it's like you asked the question I wanted someone to ask. So yeah, what happens if you have an equation where your term, you have something written in upstairs, but you need it written downstairs? What do? And the answer is the metric tensor. The metric tensor is what kind of saves the day for you. So how does that work? Well, let's say this is actually one of the crucial fundamental ideas in tensor analysis. And we'll call it raising and lowering indices. So for instance, say you have the vector v lambda, but you want the vector v, you want the covariant components of the vector. So you have the contravariant components v lambda. So let me write that out. You have, but you want this thing. So maybe you want that because you need to take that object and use it to measure something or calculate something. So what do? So you have this thing, and what you do is you take your contravariant components of your vector v, and you multiply them by the covariant matrix. Sorry, covariant metric tensor. We'll go with, this is lambda, we'll go with mu lambda. And the end result of that is you end up with the covariant components of your vector v. Now the subscript is different, but the subscript is a dummy subscript. It's just saying it's a variable that we're going to be maybe summing over, or you're using to pull out the specific components of that covariant, the specific covariant components of that vector v. So the fact that we ended up with a slightly different looking thing doesn't actually matter. This and this are the same. So we use the metric tensor to raise and lower indices. So if I have a to the gamma, then if I take that and multiply it by g gamma lambda, that equation will equal a to the lambda. the fact that the metric tensor allows you to measure lengths and angles and pull out different components of whatever vector or tensor you want, the metric tensor is incredibly powerful and incredibly helpful. You might be wondering to yourself, what on earth is this contravariant metric tensor? He never told me anything about this thing. And the contravariant metric tensor is the covariant metric tensor, the inverse of it. And so what's the contravariant form of the metric tensor in polar coordinates? Well, let's see here. We'll go back to polar. We know that G gamma lambda in polar coordinates is 1 r squared 0, 0. Therefore, G gamma lambda is equal to 1 over r squared 0, 0. All right, more questions. I think this is probably quite new, or at least a different way of thinking about things. So I encourage as many questions as you can throw at me.
Just to clarify, I understand, when you switch the subscript and superscript, you're basically saying you're changing what you're measuring, I believe.
Yeah, so I think of it this way. If we're used to measuring, I think, contravariant components of a vector, in which what we do is we look at the projection perpendicular to the basis vectors. So we have our vector, and then we find something that's perpendicular to our basis vector to calculate the components in that direction. And that's the way we calculate contravariant components of a vector, is we look at, we project that vector perpendicular to the basis vectors. The covariant components of your vector are found by a parallel projection of your vector onto the basis vectors. And so you're kind of switching how you're measuring it from measuring it with a projection that's perpendicular to your basis vectors versus a projection that is parallel to your basis vectors. In Euclidean space, those are the same. In any orthonormal, in any coordinate system that is orthogonal, that is doesn't matter. But if you have any curvilinear system, coordinates on a shell, coordinates that are simply deformed, like if I just take an object and I stretch it, the material kind of points are moving with that system. And so I'll be looking at how do I measure things in that new world. And so the covariant and contravariant components of a vector are kind of like saying, how am I measuring this? Am I measuring this based on quantities perpendicular to my basis vectors or parallel to my basis vectors? And the vectors themselves are basically just telling you, I have some vector, and how does that vector transform as I change coordinates? So how, if I know it's not changing at all, how will the components of that vector change as I switch things around? And that goes back to like the velocity discussion before. Does that help or answer your question?
Yeah, I think that answers it.
Other questions?
What would G with say gamma in the lower index and lambda in the upper index look like? Like I'm a little bit confused on what tensors with both lower and upper indices mean.
No, that's a fantastic question, and it's definitely something I struggled with for a while when I was learning this. So those are what are referred to as mixed tensors, and this is probably an annoying way to describe it, but it simply means that the components that you're asking for, some of them are covariant, some of them are contravariant. A better way, perhaps, to answer the question that you're getting at is to say, okay, I'm sort of comfortable with this, maybe. I'm sort of comfortable with this idea. I'm going to copy it. So I took and I dotted two covariant basis vectors into each other, and I got the metric tensor. I can similarly dot the contravariant components of my basis vectors and get the inverse of the metric tensor, or the contravariant metric tensor. Now, I think what you're asking is like, well, what happens if you just took G mu dot G nu? And so in this case, I'm dotting the covariant components of the basis vectors into the contravariant components of the basis vectors. And I don't think we're going to have time to do this derivation right now, but what this results in, always, if you for the metric tensor, if you're dotting the covariant and contravariant components of the metric tensor together, what you end up with is Kroneker's delta. And why would you think that? It's kind of like saying, for the first component, I'm taking, let's look at just the this part of it, the r squared part of it. I'm kind of saying I need r squared, and I need to dot that into 1 over r squared. And so that component becomes 1. Or if I look at the spherical components and I say, I have, in my covariant form, I have r squared sine squared. My contravariant form would be 1 over r squared sine squared. So those two components of my metric tensor, covariant and contravariant, dotted into each other, cancel each other out, and become just the Kroneker's delta. I forgot to write that this is Kroneker's delta. The identity matrix. Does that help?
Yeah, that doesn't make sense. But I'm also just, so like looking at the valid tensor equations section, you have, let's see, like U, where is it? U sub m superscript k, and then that equals v with I in the lower index and k in the upper index. And then like you wrote below that as an example, like S with L in the lower index and MN in the upper index. I'm having trouble sort of understanding like what those mean as well. Like for example, are U sub m superscript k, like is that Kroneker's delta?
No, that's only, the thing I just told you is only true for doing that for the metric tensor. So let's unpack this a little bit. Let's take, well, actually I already grabbed it in brown. So let's grab it and pull it over here. Okay, so I have this thing. I don't know what it is. It's some awful S. Actually, let me do it with a second order one, because I feel like I can at least conceptualize second order tensors. So let's take our RIL. And let's properly change it to a mixed tensor. I would take that and I would say, well, I'm going to multiply that by G, my metric tensor. And I would like to raise the index L. And in order to do that, I have to change it to something. So I'll change it to K. So the result of this is these L's are going to contract. So I'm not going to see L on the right-hand side. I'm going to get a new thing, but we'll call it R. And it's going to have I as a covariant component, and it's going to have K as a contravariant component. This is a mixed tensor, and what it means is if you're grabbing kind of something like R1, 2 or R1, 3 or R1, 1 is that the first kind of component you're grabbing would be the covariant component, and the second one, the 2 or the 3, would be the contravariant, the inverse of that vector's, that tensor's, the covariant component of that, sorry, the contravariant component of that tensor. I struggle and have always struggled with trying to physically interpret mixed tensors, and I think they're typically used to kind of write notation more compactly, and then what you often do is kind of say, well, I don't know what on earth. You often kind of do the opposite. You say, well, I don't really know how to write down the components of this mixed tensor. So what I'll do is I'll use the metric tensor for the coordinate system that I'm in, or that I would like to be in, and unpack it and go back to this way. And so I kind of think of the mixed tensor as saying, tell me what coordinate system you want to be in, and then we can unpack that information once we're there. So I can say, I have this tensor Rij, or Rik, and I'd like to evaluate it in spherical coordinates. So what I'll do is I'll use the metric tensor in spherical coordinates to lower that K index, and then I will look at my tensor RIL in that coordinate system. And so I think of the mixed tensor as a way of kind of not carrying around the metric and saying, okay, here's a tensor. Tell me what coordinate system you'd like to evaluate me in, and then we'll use the metric tensor for that coordinate system to grab the components RIL, which would be covariant or contravariant. There's other ways you can do this, and I don't. Maybe I can draw this up or point you to something, but like you can construct these things less symbolically if we just kind of write down our tensor in one coordinate system, and then we use a metric to kind of raise one of the indices. And it comes down to kind of stuff that you did in linear algebra, where you're taking a matrix and you're multiplying it by something that's sort of like an identity matrix, but not quite. And as you're starting to do this matrix manipulation, multiplication, you can take that tensor and write it in covariant form, multiply it by the metric tensor to get it how it looks in its mixed form, multiply it kind of again by the metric tensor to get how it looks in its contravariant form. I wish I had written down an example of that, and I don't want to screw it up here, which I certainly would. But it might be helpful to think of it in those two ways. One, you're kind of you kind of left the unpacking of that mixed tensor to whatever you're going to evaluate it, whatever coordinate system you're going to evaluate it in. And two, we could look at RIK if we kind of knew what it looked like in one coordinate system. Maybe we know what it looks like in Cartesian coordinates, and so then we could use the metric tensor to kind of raise some of it up and look at it in that mixed form. that's probably too big, and so I'll try to send out a more like matrix multiplication example of this. I think I might be able to cook one up in Mathematica, so you can see like what those components look like in the covariant, contravariant, and mixed form. So I'll try to do that in Mathematica for you.
Thank you. Yeah, and I think it makes a little bit more sense.
Yeah.
Yeah, but thanks.
Could you, is it valid to say that that R sub I K is the dot product between a regular sort of vector in I and an inverse vector in K?
Yeah, I think that's fair. Yep. I don't know if that clarifies it to others. I think you could think about it in that sense. And so I get a little bit dubious with thinking about kind of like column vectors are fine, but row vectors, we often learned about column and row vectors in kind of a lazy way where we could just kind of like flip them, you know, and everything's fine. Like if I have a column vector that's 2, 1, and I flip it to a row vector that's 2, 1, like nothing really changes. But that's only true if you're in Euclidean space. And so I'm always
Yeah, I guess I would back up and say that when I said vector, I didn't mean, you know, Euclidean vector, just a vector in general.
okay.
So like the BI, I don't know that gives any more visual or physical intuition, but at least to
For
make
me,
sure.
it's always helpful to see that, and I know it's kind of tedious and it's almost like against the spirit of it all, but to me, it's really always helpful to kind of see all of the tensors like unpacked. And that's really only possible for like these second order tensors, because third order tensors are kind of like a 3D array. And fourth order tensors, I don't really have any way, I don't know how to conceptualize them. I just kind of use them as mathematical objects. When I was learning all this stuff, a wiser colleague of mine basically told me to like stop asking all of the conceptual questions of like, what does this mean? What does that mean? And just learn the rules first. Like, just like, okay, how do I go from A sub I to A, you know, with an I in the subscript? How do I contract these things? How do I multiply these tensors? How do I do like some calculus operations like a divergence or a gradient or a Laplacian in this framework? And he was basically just like, stop asking those conceptual questions, learn the rules, and then go back and figure out like what is happening. And I hated that advice. And so I'm not passing it on to you. I'm just saying, I think he might have been right. I think it's kind of like learn the rules of baseball and then like go back and figure out why they threw a curveball on that pitch there. And I think that's probably a fair way to think about this, is like trust the process a little bit of just you're learning a new way of doing math. And so at some point to start, it can just be helpful to just, all right, I'm going to take these rules and run with them and see what happens. And then I can go back in and try to physically conceptualize these things. Now, I don't think I really did that well. And so I still kind of bumble over trying to conceptualize some of these quantities. But I just passed that advice along because it probably would have sped up my learning had I just taken the advice and stopped being like, what does this mean? But yeah, so I passed that along kind of with a grain of salt. All right, that was a lot. It was a real crash course in tensor analysis, which tensor analysis allows us to describe how things transform when we change coordinates. And that is essential for us to be able to describe how to measure and do calculations and do calculus on our various arbitrary manifolds. And that's what we'll start to talk about next class. It'll again be another crash course, but my hope is that it leaves you with a little bit of less fear if you see this stuff and like, okay, I can kind of start to wrap my head around what I'm seeing there, because I think that is honestly most of the effort. Is if we can get past the what on earth is this, I'm not going to look at it, you can do pretty powerful things with this mathematical framework. All right, thank you everyone. Sorry for going late.